Hello everybody. So now we are going to see if we have a case where the information that are given are not quantities, and I know just some information about the concentration or composition as mole fractions or mass fractions, and I want to use them to get the other one. And either I know mass fractions and I want to get the corresponding mole fractions, or the other way around. So if the quantities are not available, we can deal with this case in a very simple way. And this simple way depends on a very basic concept. And this concept is that the composition or concentrations are independent on quantity. This means that if you have, for example, let's say you have seawater. You went to the sea, you have the whole sea that's filled with huge amount of water, and you took a cup of and filled it with the seawater. Okay, so you have the same water in the sea and in the cup, but the cup is small amount and the sea is big amount, and you want to calculate the composition or the mass fraction. Let's say the mass fraction of the salt in water in the sea and in the cup. What you'll find is that it's the same for both. The concentration or the mass fraction of salt in the seawater is the same as the mass fraction in a small cup filled with the same seawater. And this is because the concentration is independent on the quantity. So whether the quantity is large, is small, is intermediate, it doesn't matter. The concentration or the composition is always the same. Okay, as long as it's the same, it's the same water or the same mixture. Okay, and this is what happens if you think about this. This is what happens when you take a blood sample. So when you want to find the concentration of anything in the blood, you don't take the whole blood of the body to know the concentration. You just take small amount, and this is enough to know the concentration in your body. So you don't have to get the whole amount of blood in your body. So this is what we base our calculations on. So since the quantity is not affecting the composition as mass fraction or mole fraction, so we can, if there is no given quantity, we can assume what we call a basis. So the basis is a word that we are going to use a lot in this course. So a basis means that you assume a quantity. Okay, and the reason you are assuming this quantity is because you need it to do the calculations. No matter what this quantity is, if you assume the quantity to be 10 grams, 10 kilograms, 100 tons, 10 milligrams, it doesn't matter. Why it doesn't matter? Because the concentration and compositions are independent on quantity. So no matter what the amount of the basis you are assuming, as long as the calculations are correct, the result is also going to be the same as mass fractions or mole fractions. So let's take another example just to clarify this. So in the previous example, we had the four components: oxygen, nitrogen, carbon dioxide, and methane, and we had quantities. Now I have the same four components, but I have it says here calculate the mole fraction of a mixture with the following mass fraction. So I know the mass fractions. Plus these ratios or these fractions that I have here are mass fractions. So 10% of the mixture is oxygen, 40% is nitrogen, 30% is carbon dioxide, and 20% is methane. And I want to calculate the mole fractions. So to calculate the mole fractions, we will not be able to do this without having a basis. So I'm going to assume any basis. You can assume, of course, the basis has to be easy for you to deal with. So since these are mass fractions, so you assume a basis of mass. Okay, you can assume basis of any value, but if it's multiples of 10, it's gonna be easy for you to do the calculation. You can assume it to be 1.75 kilogram, for example. But then you will make it hard for you to do the calculations. While if it's multiples of 10, it's going to be easier. So if I assume a basis of 100 grams for the total mass, then I know that this 0.1 is the mass of oxygen divided by the total mass. So I can calculate the mass of oxygen as 0.1 multiplied by 100. And this is why it's easy to deal with multiples of 10. Either it's 10, it's 100, it's 1000, it's going to be easy. So oxygen is going to be 10 grams, nitrogen is 40, carbon dioxide is 30, methane is 20 grams. Now it is the same as the previous problem. We know information about quantities and we can use them to calculate the mass fractions or mole fractions. So in this case I want to calculate the mole fraction. So the same procedure that we followed before. In order to calculate the mole fractions we need to have number of moles, and in order to have the number of moles from masses we need to have the molecular weights. The molecular weights were already calculated in the previous example, so I'm not going to do this again. So for each one of them I will divide the mass by the molecular weight. So it's 10 divided by 32 for oxygen, it's 0.31 gram mole. Nitrogen is 40 over 28, carbon dioxide 30 divided by 44, methane is 20 divided by 16. So now I have the number of moles of all the components, and now I can calculate the total number of moles, which is the sum of all of them. And from the individual number of moles and the total number of moles, we can calculate the mole fractions. So it is 0.31 divided by 3.67, 1.43 divided by 3.67, and so on. So now we calculated the mole fractions. Again, I put it in the form of a table. So these are the molecular weights, these are the components, the molecular weights, the mass fractions, and this is the basis that I assumed, and from the basis I calculated the masses. Again, having them in a tabulated form makes life much easier. And then the number of moles that we have as mass divided by the molecular weight, and finally we have the mole fraction as mass divided by the total mass. So it's very, very straightforward. There is one thing that you can do is we can skip this basis assumption by doing some mathematical manipulation to the equation. So this is the equation that we saw last time, and if you divide the numerator and the denominator by the total number of mass, the total number of moles, you will get n over n total, Na over n total in the numerator, and Ni over n total in the denominator. So you can have this equation here as Ya multiplied by molecular weight of A divided by the summation of Yi divided by molecular weight of I. This is one way to do the calculation without the bases. If you want to do this, it's fine. If you want to go with the table, it's fine. The basis is more straightforward. It doesn't require a lot of calculations in the same place like here. This is kind of easier if you want to do this in only one step. So this is going to be one step. You calculate XA and then you're done. The same for mass fractions to mole fraction. You can start with this equation, n over n total, which is Ma over molecular weight of A. You can divide up and down by, or the numerator and denominator, by m total. So you have x over molecular weight of A divided by sum of x divided by molecular weight of I. Anyways, this is an extra thing. If you want to do this, it's fine. If you don't want to do this, go with the basis, which is a more systematic thing to do. I'll stop here. There's only one thing left that we will discuss next time, and which is the average molecular weight, and just a quick revision on what we mentioned here in this chapter. So I'll see you next time, inshallah. Goodbye.